So in our lesson, we have a brief outline. We have to introduction to inferential statistics. We have to know about confidence interval, meaning that of what confidence is the researcher of the report is saying concerning the sample. Then hypothesis testing, correlation tests, and regression. So all these are covered under inferential statistics. So as an introduction, so as I said, inferential statistics use a random sample of data selected from the population. And this is used to make a generalization about the population behavior. So it is an estimate of the population based on the information that is gotten from the sample. So, and from there, conclusions are drawn about the relationship or association between variables and about the designed hypothesis. So they are designed to test for hypothesis. In inferential statistics, there's always a confidence interval. So this is always a confidence interval is talking about the margin of error that can be ascribed to the results. For instance, so if a researcher studied a sample of a population, because the entire population is not studied, there is a possibility of an error margin, maybe error of omission, error of commission, error of inadequate sample, error of this. So because of that, there's always a margin of error to make your result acceptable. And that is what brings about a confidence level and our confidence interval. The confidence interval explains that within a particular region, to the average, the estimate mean of the sample, at least 95% must fall within a region. And if that is the case, the result or the decision made will have been judged as being fair and of the confidence level. What it means is that if you are repeating the same exercise, the same thing within the population, 95 times out of 100, you'll be getting the same value. What does that mean? If you am to study, for example, if I'm to study the students of UM, if I'm selecting sample of 100 students, so what it means is that if I select samples and I got their mean or got their informations, then I select another sample, get the information, I select another sample, get the information, it means 95 times I will be getting the same result. So irrespective of the people I am investigating, so far they are students of UM, it means if I select different 20 samples of the same number, the result I will get from them will be 95% the same. So the error level of 5% is allowed. So, but in medical research, most of the time in medical research, the error margin level is 0.1%. That means 1 in 1,000 times wrong. That if you have done something 1,000 times, you can only be wrong 1 time because of the precision of medical sciences. So the margin of error is so small that in fact, a mistake is not expected to happen. But in social sciences, a margin of error of 5% is judged adequate. That means 95 times correct. So if you are doing the same thing 100 times, 95 times you have to be correct. It will be the same, you will be getting the same results. So a 5% margin of error is allowed in social sciences studies. So still about confidence interval. The confidence level it is estimated. Most of the time there will be an estimate of what the range is confidence interval. So most of the time when we have our population samples or our N and we know the average mean, to achieve variations, we know where our variation should be within. So, and this equation here is telling us that when we know our mean, we had plus or minus a z-score multiplied by the standard deviation of the mean divided by the square root of the population or of the sample, will give us a acceptable variation level. Let me explain that with this chart. Remember last time we talked about standard deviation. So here, our 95% interval will give us a sample mean plus 1.96 is a set score for 5% error margin. It has been worked, it's statistically worked. Multiplied by standard deviation divided by square root of the sample. So this is the set score, set at alpha 2.5. So alpha divided by 2, that is 5%. Our alpha is 5% divided by 2. So set score at alpha divided by 2 is 1.96. Then multiply by the standard deviation divided by the square root of the sample. So now, when we get here, what it shows is that our 95% confidence interval will be within the margin of mean plus 2 standard deviation. Remember, we tried to illustrate this that the standard deviation is giving us the acceptable variance, how dispersed with the result we are getting B from the mean. So what it's saying is that with 95% confidence interval, which is 5% error margin, the sample mean, the result we are getting from our sample, 95% of that result will fall within mean plus SD, 2 times SD, which is the same thing as mean plus 1.96 set score standard deviation divided by sample. So this is just reimbursing that the 95% error margin level falls within our mean value plus 2 standard deviation. So if the standard deviation, by the time we had 2 standard deviation, if it is less than 95% that are within that score area, that means the sample, the decision from the sample is not, the confidence is not there. It has a low confidence. But at least if 95% of our results fall within this range, then we are confident of what our result is, and whatever we do, our inferences will be relevant. So before I move on, I want to, do we understand the confidence interval? Confidence interval is just giving us the area of coverage of our scores, where they fall in. If 95% of our score fall within that range of mean plus 2 standard deviation, confidence is increased. Any question about confidence interval? Any question about confidence intervals? It's just an area of, it's just an area where we have majority of our observations of our scores, not too dispersed away from the mean. So we'll be able to be sure that the result we are getting is 95%. We are 95% sure. We are 95% confident that this course or the result we have gotten, when we analyze the data, whatever we get out of the data will be relevant and will be reliable. So that is what the confidence interval is saying. So by this, in statistics, in inferential statistics, this confidence interval try to measure how significant our result is. If it is significant, then we are good. If it is not significant, we'll be able to show that. And that will lead us to hypothesis testing. And that is where when you hear the word significant or whatever, you will be able to understand how significance is evaluated, whether it is in support of a decision or against a decision, depending on the hypothesis we are testing. So I want us to get this one clearer, because if COVID-19 goes down by the end of this year and you are to collect some samples in your project, you may need to use confidence interval or significance level in your analysis of your data, even if it is going to be a secondary data. There is a way of measuring the significance level of the data relationship. I hope I am clear.
Doctor, I have one question.
Yes.
Why the formula given is plus minus 1.96?
Okay. Yeah.
No.
Okay, the plus minus is saying about, when you have a mean and let's say the average age of everybody in our class is 22. Let's assume 22 average, that is the mean. So and when we say plus or minus 1.96, what we are saying is that majority of those 95% of people in that class, in our class, will be 22 years old plus 1.6 or 22 years old minus 1.96. So 95% of the people in the class will fall within that bracket. So a set score is determined to show us the dispersion around the average age. So what we are saying is that maybe the least person, the youngest person in the class, will be 22 years minus 1.96, while the oldest person will be 22 years old plus 1.96. So what we are saying is that the age bracket of everybody in the class, 95% of people in that class, will fall within that bracket. So if that is true, then the average mean we have selected of 22 years is perfectly reliable. Does that answer your question?
What I mean is how do we get that 1.96?
No, it's a different calculation on its own. It's a z-score calculation on its own. So when we try to study different tests in statistics, because we have what we call z-score, we have t-statistics, we have f-statistics, all those things they are real core statistical calculations. So which we need not to bother ourselves about, but we just need to know how to apply them. So it is calculated as a z-score based on the confidence interval. So there are some statistical calculations that leads to that. And not only that, the t-square, the chi-square, all those figures are calculated. Pure statistics. So our scope is just to know how to apply them, to know our ranges of what does it translate to in our study. And one way of using it is to determine the confidence interval in our studies when we have collected a sample. So it's just an application here.
Yes, thank you, Doctor.
Okay. So are you still seeing my screen? So we go to test of hypothesis. Normally, hypotheses are statements of explanations as made on basis of a limited evidence as a starting point for further investigation. So if I make a statement that every student of statistics of BIX1004 had a university diploma before starting their degree course. You know, it is possible. Some people do diploma, some people come in from high school, some people has done one program after secondary school or the other. Some did A levels. But if I just use a statement that students in the class are all has diploma, fine. But that evidence is limited. I might not be sure whether all of them has that, or whether many of them have that. So that is a statement of hypothesis. So if I want to express it in an hypothesis form, hypotheses are always expressed in negativity format, like not, like did, not, like insignificant, not significant. So I would like to say that such a statement will not be a true statement until it is tested. Do we understand that? Will not be a true tested on a true statement until. So we can now collect data in order to put the hypothesis into test. So when we put the hypothesis into test and it is either significant or not significant, then we can take a position. So here, the position is that we want to test whether everybody in class has diploma. So if I want to express the hypothesis in a negative form, I will say not everybody, every student of BIX 1004 does not have a university diploma before coming to the university, or does not have a diploma certificate before coming to university. Then I begin to collect data from all of you, asking you what were the certificates you are holding before coming into university for degree program. So the statement, the data I'm collecting from you will give a direction whether majority has that or not. If only a few of students has diploma before coming for the degree, then that means it's not majority, and that will lead to either rejection or acceptance of the expressed hypothesis. So for example, in statement of hypothesis, we talk about life is boring and nothing is exciting. So to some of us, life is boring and not exciting. Some people, life is is enjoyable. So I've taken a statement that life is boring and nothing exciting. That's a negative statement. For another one is I can say student mean IQ is not beyond 120. So if IQ is rated and I say students mean IQ or student IQ is not beyond 120, perhaps rating of 120 may be too low, maybe a low IQ, maybe medium or moderate, or maybe a IQ level. So we will look at data, that what kind of data will give us an answer to that question. Then we'll now look at it whether the IQ is beyond 120 or not. So we measure the IQ of a lot of students. So for every null hypothesis, we call it null hypothesis H0 because it is expressed in negative form. So for every null hypothesis, there must be an alternative hypothesis to either accept or reject. So for example, if I say life is exciting and full of fun, then life is boring and nothing exciting. So one is negative. The alternative hypothesis is that it is full of fun and it is exciting. So if I said student IQ is less than 120 or is not beyond 120, I can also set an alternative hypothesis of student IQ to be excellent, meaning they are higher than 120. So excellent IQ. So testing of hypothesis and insignia can be conducted using various statistics. So I can now collect data from the sample or from the entire population if they are not too big, and I slot it into my analysis, and my analysis can tell me whether the IQ is excellent or not. Which one do I reject or which one do I accept? I hope I am still talking. Is that understood? So, do we understand the way we express hypotheses? Class, do we understand the way we test hypotheses or the way we express hypotheses before we go into testing?
Yes, understand.
Okay. Yeah, so let's now look at various ways of testing for an hypothesis. Here, one, set score. So for the person who asked for the set score the other time, so this is how to assess the set scores. So most of the time, the set score is expressed with this formula: x minus mu all over standard deviation divided by square root of n. So this one gives us the said scores, the said statistics. When we do set test in the statistical test, we use this expression to find our set score. X is the sample mean, mu is the population mean, standard deviation is the standard deviation of the sample, and n is the sample. And you know standard deviation, but divided by n is the standard error. So these are statistical analysis. So we have, when we are given a sample mean, then the population mean will be given. And when we use this expression, we find what we call said scores. So the set score will be used to judge whether the hypothesis, if the set score is significant or not, will tell us whether the hypothesis should be rejected or should be accepted. So most of the time, set scores or set statistics are used when our sample is larger than 30 or is from 30 and above. When the sample is large. For test of hypothesis, a sample of 30 and above is considered a large sample size. But when it is less than 30, we use what we call T statistics. So the same thing, the same expression, but the only difference is the sample size. So when it is bigger than 30, we talk about said statistics. When it is less than 30, the sample is less than 30, from 1 to 29, we say we use T statistics. So it is the same formula that is being used, either Z or T. But the difference is about the sample size. So when you get the T test or the Z test, there is a level of significance. So when it is significant, we can reject our hypothesis. When there is not significant, we can accept our hypothesis. So another way of testing hypothesis using T statistics, we have what we call independent sample T test. So where means of two groups are considered. For example, if you want to look at the class, information about the class, we have two genders. We have male, we have female. If we want to know the mean for the female responses and the mean for the male responses, is independent sample T test can compare the mean between the male and female. So if there's no significant difference between what the two groups are saying, then we say we can lead to a rejection or acceptance of an hypothesis. For example, if we say female students are more brilliant than male students, that's a statement of hypothesis. Female students are more brilliant than, or you can say female students are less brilliant than their male counterparts. So we collect the results of everybody in the class. When we find the average mean of the scores from the male, the average mean from the scores or results from the female, there is a way of doing the sample test by cross-checking the t-test between the two of them. So if the means, there's no significant different mean in their scores, then we can reject that they are equally brilliant. But if there is a very significant difference is reported, then that means they are either less brilliant or more brilliant, depending on statement of our hypothesis. So we look at this. That is a way of independent sample t-test. Means of two groups, because when you are doing t-test or z-test, we are trying to see what is the deal, how does the mean reflect the population? The means of the sample, how does it reflect the population? So then there's what we call peer sample test. So here in peer sample test, it is the same group, let's say the same male, but you want to know, you now pair their samples into two. They are all male, then you divide the results into two, you classify them into two, check the result of this, check the result of that, and look at if there's any difference between the group. So they are the same group, but are there differences when you pair them into two? Are there differences in the result coming up? So if there are differences, then you'll be able to know whether it's significant or not. Then there's what we call one sample t-test. So this one compares the means of a group with an already known mean. It's not that you are comparing the mean freshly. For example, if you want to do that, let's say we already know the mean of people in this class, and we want to compare it with a new set of information. The already known is compared with newly collected samples. So that's why they call it one sample t-test. So all these are trying to lead us to the level of significances of the differences in the mean. If the differences in the mean is not wide, it's not significant, it leads us to a decision making in statistics. So then another test of hypothesis is what we call analysis of variance. ANOVA, you will be hearing about ANOVA. Instead of t-test, ANOVA use F-test. So F-test is conducted especially when there's a regression. So when there's a regression between groups, variability between groups that are in the larger society is observed. And when you compare their means, if there's any significant difference, we'll be able to report. In fact, ANOVA is more useful when we come to regression. Most of the time when we are talking about the level of significance, there's what we call a p-value. P-value is talking about the error level to be less than 5%. If the p-value is less than 0.05, which is 5%, then we say it is significant. So if there's a significant effect, the null hypothesis is usually rejected because the null hypothesis is expressed in negative, showing that there's no significant effect. Something is not significant. But if our analysis shows it's significant, then we reject the null hypothesis. I think we'll put this one into more contextual position when we try to do some regression or correlation test. So then the decision rule when we are testing for hypothesis, there are decision rules. For example, this rule leads us to either accepting or rejecting our hypothesis. Possibility of having a type 1 or what we call type 2 error in statistics. What it means is that there can be a true hypothesis that is going to be rejected, or a false hypothesis that is going to be accepted, depending on the analysis. And if that happens, we have either type 1 error or the type B error. So to make it simpler, look at the reality, the chart I have here, the reality, the table I have here, there's a reality, there's a test. For example, when there is a false hypothesis. So let's look at what would be a false hypothesis. Let's look at a statement that we know is not correct. Okay. Let's look at the hypothesis that underage. Well, what can I use? I want to look at a statement that will be false, that we all know could be false. So let's see, an underage will not be allowed to drive in Malaysia. Okay, an underage will not be allowed to drive in Malaysia. We all know that an underage will not be allowed to drive, correct? Let's assume that that's our statement. Underage will not be allowed to drive in Malaysia. That is true, because when you are not up to a certain age, you will not be allowed to drive. But supposing we collected the data from the drivers, those who are driving cars, who drive cars in Malaysia, and we discovered that underage are so many among them. You know, it is possible when you test the hypothesis say underage will be allowed. You know, that is a true hypothesis, but that is being rejected. So if it is now rejected at underage, it is now found that underage are more among the drivers. And it significantly shows that underage are more among the drivers. That means a true position is being rejected. And when you reject such a true position that underage should not drive, but eventually you find underage driving, so a true position has been rejected. And that means type 1 error has been committed. But at the same time, when something that should not be done is found being done, accepted, it is what we call type 2 error, because a false position has been accepted as a normal situation. So that is what the responses from investigation outside can create. So if that happens, type 1, type 2 error can come in. But the best thing is that an hypothesis is stated, and if it is a false hypothesis, if it is a true hypothesis, it's supposed it is accepted. When a study is conducted and a true hypothesis accepted, while a false hypothesis is rejected, then we have a correct position, either correct rejection or correct acceptance. But if it is the other way around, that what's supposed to be false is accepted as true, or what is true is now rejected as being a false, then there is either type 1 or type 2 error. So most of the time, the data we collect will let us know whether the position that is supposed to be true is true, and whether the position that's supposed to be false is false. Am I clear with this?
Yes, doctor.
Okay. So now, where do we use all these hypothesis jargons? We use it when we are looking at the correlation and doing regression. So that takes us to our next topic, which is talking about correlation and regression. So when we do correlation studies, our softwares that are available will give us the either significant or the level of significance or not. So when there is a level of significance expressed, then we will be able to say that no, this is impactful, this is not impactful. So this takes us to correlation and regression. So under correlation measures the degree of association and relationship between two continuous variables. So when we say two continuous variables, we are talking about, for example, let's think about age. And okay, let's look about age. Weight and height. Let's think about weight, height. You know, you can measure weight continuously. So also we can measure height continuously. So they are both on the same degree, or they are the same type of data. So we can talk about the relationship being between the weight and height of a person. So if I want to do that, let's say we are postulating that the taller the person is, the heavier the person is. You know, that may not be in all cases. That the taller you are, the heavier you are. Some people are short, but they have more weight. So we can look at whether this statement correlates. The heavier you are, the taller you are, or the taller you are, the heavier you are. So along other way, we can look at other statements that will look at a relationship or association between two variables. I've just talked about a variable, the height, and the variables of height and weight. Then there could be another one, like when we are talking about unemployment rate, and deprivation. For example, when we are talking about unemployment, social deprivation, do they go the same way? If you are unemployed, does it mean you are socially deprived? Or if you are socially deprived, does that lead to no employment? So we can get the level of unemployment and deprivation. So if unemployment is 13%, so what level of social deprivation shall we be expecting? So this can be done through correlation. Again, does the private reading time of students affect their examination grade? So we are looking at these statements that, as students, if you have more private time to read, does it really affect your grade? For some, the more they read, the more understanding they are, and the better their exam grade will be. For some, being in class alone gives them all the examination grade they want, and is good. It is only when they are not in class, no matter the level of private reading, it may not give them grade. For some, they will be in class, they will still read more, then they have good grades. For some, they may not be in class, only read private reading time, their private reading time is being scheduled, and it gives them grade. But generally, everybody we believe that when you have a private time to read more of what you have been taught, you are likely to have better and higher grade. So that's why we can come out with that statement. Either like private reading time of students does not affect their examination grade. So your private reading time does not really have effect in your grade. So when we collect data about reading time, then about the examination grades, then we can correlate the two together. When you correlate them, we'll be able to see whether one is affecting the other, and we will see the direction of effect, whether it is affecting negatively or it is affecting positively. So when we correlate such thing, when we say correlation, we are looking at the degree of association or relationship between two variables. Now, then another one is, we talk about the level of female education in developing countries determine the number of children they have. For example, in some countries where females the more the females are educated, the less the number of children they have. Is it possible? For me, in my country, when you go into the rural areas where people are less educated, so they can have any number of children they wish to have, especially when they are not exposed to birth controls or what they call family planning somewhere else. So they are just living their life. But in the cities, where more people are educated and they want to control their finances, and when they want to know they are giving the best to their children, they determine the number of children they will have. Some may say 2, some may say 3, some may say 4, some may say 1. But in the rural areas, you can have a woman, a female, having 6, 7 children. So let's look at such a study that the level of education determines the number of children. So you can collect a lot of data from females who are married, ask them their level of education, then the number of children they have. So we can look at that. So if the level of education determines the number of children you have. And in what direction? The higher your education goes, the less the children, or the higher your education goes, the higher the number of children. So all this can be explained, and they can be explained in the scatter diagram. So this diagram that I put down here is talking about the various ways the data collected can be plotted in a diagram. So when you have collected the data from a lot of samples, looking at the figure in the left, so you can see how it is distributed. So the first one of the figures in the left shows that perhaps maybe the higher the number of the higher the level of degree of education, the higher the number of children. That is a positive way. That's a positive relationship. The higher the number of the level of education, the higher the number of children you have. So that's a direct relationship. It's a positive. To say one is increased, the other is increased. Then the next one there shows a negative, the one that flows from left to right in a downward relationship, shows that when one increase, another one decrease, or when one decrease, another one increase. Meaning, the lower the level of education, the higher the number of children female have. So this relationship, so what I'm trying to say is that correlation can exhibit a relationship that is negative or a relationship that is positive. So again, the relationship can be completely linear, a straight line, while on the other time, it may not be completely linear. It can be a curve relationship. No matter either negative or positive, it can look like a curve. And again, there may be no relationship when they were just scattering, like forming a circle. So if the relationship is like forming a circle, it shows that there may be no relationship. So if there's no relationship, then we say that the slope of such curve will be 0. When it is perfect 1, then there's a very, very sharp relationship. And the line will just be like one straight line, either fully horizontal or fully vertical, depending on the direction. So the picture on the chart on the right hand is talking about size. How do we measure the size effect? So the size effect, in the sense that whether the correlation is weak, whether the correlation is moderate, or whether the correlation is strong. So these are judged by the correlation coefficient. We will talk about that also soon. So in measuring correlations, so correlation ranges from -1 to +1. So perfect positive correlation will give you +1, while perfect negative correlation will give -1. When there's no association between two variables, you have 0. So when it is between -1 and 0, we have negative. And when it is greater than 0 but less than 1, we have positive. So since correlation is a relationship between two variables, a linear association is expected. And that's a close data point to a straight line. So when we look at the figures here, the previous figure, we can see some of these charts giving us a close association along a straight line, that the data points clustered along a straight line, either in the negative form or in the positive form. So this is the line of the slope. So correlation coefficients. You know, I said either the correlation is strong or the correlation is weak. Rate is being calculated by the correlation coefficient. So this is the equation for calculating the correlation coefficient. Here, the correlation coefficients can be this formula. I have two formulas here. One is what we call person product moment correlation coefficient, while the other one is for Spearman rule correlation coefficient. Let me explain the difference between the two. The person product moment correlation coefficient is used when we have a parametric test. What do we mean by parametric test? We mean that the data we are using are normally distributed. And when they are normally distributed, when we look at our chart under standard deviation, you see when they are normally distributed, almost equal half of the data will be to both to the right and left side of the mean. So let me quickly recall that. I want to use this chart, this confidence chart here to illustrate what we mean by normal distribution. So the mean is in the middle, remember, mean. So what it means is that if the data is normally distributed, almost half of the data will be to the right side, while almost half of the data will be to the left side of the mean. So it will be a normal. When it is more to one side than the other, it is non-normal distribution. I think that gives us an idea of what a parametric test means. Parametric tests are conducted on normally distributed data. For Spearman rule correlation coefficient, when data are non-parametric, when they are not normally distributed, especially when the data are ranked, there may be need to use a non-parametric correlation test. So when we get to research methodology and all those things, you understand more about parametric and non-parametric tests, because every data that is ranked that doesn't have equal distance between themselves are regarded as for non-parametric test. For example, if you have collected the data where you have to rank the responses, maybe level of agreement. If you have gotten the data about level of agreement that you rank strongly agree. I hope you have been, I'm sure you have been filling some questionnaires that will indicate your level of agreement. Strongly agree, undecided, disagree, strongly disagree. So data were ranked, such responses were ranked. And the only thing is that the difference between agree and strongly disagree may not equal to the difference between agree and undecided. So they don't have equal interval among themselves, the ranking, but one differentiates the other. So in such a ranking data, it is better to use a non-parametric test to show the correlation. All these are built into the SPSS when you are doing correlation. So we'll be able to choose whether we want to do a parametric test or a non-parametric test, depending on the data, on the measurement of the data that we are using. So if you want to calculate it, we may have, for example, in the real estate, where we belong to, we may have a data that has to do with the size, let's say the size of accommodation, the size of property, especially when we are talking about housing, the square feet, the size in square foot has a contribution to either the rental value or the price. What do I mean by that? Let's say we are talking about having a square foot, maybe 50 square foot accommodation, and the rent or the price, 80 square foot, 120 square foot, and on like that. So when we have this data and we know the square foot with their prices, we can work out what is the relationship between the two. How much effect does the square foot has on the price? So if there's one square foot increase in the size, by how much will the price increase or decrease? So depending on the change in the square foot. So we can work it out using these formulas. This formula I've displayed to calculate on ourselves so that we know step by step how it is calculated. But at the same time, knowing this formula is just for us to have a background idea of how they are calculated. Today, we have varieties of softwares that we just tell to do correlation for you, and it will do that. So we will experiment that because there's I will have to introduce us to SPSS, which is the common software for questionnaire service, like another instrument we use. There are other software that we do correlations to. Excel do correlations too, but when it comes to non-parametric and other parameters, I think SPSS do better. Then there are other econometric softwares. When the data you are collecting is strictly interval or scale data, they can do the correlation. So, but we will maybe on Thursday, I'll come up with the data for us to experiment calculations of correlations coefficient. So that when we have we know how to calculate the correlation coefficient. It's just a relationship between the two variables, the x variable and y variable. So we follow this formula and we get a correlation coefficient. And if we have a data that is have to be ranked, we will use Spearman rule will be okay. Actually, they are all saying the same thing, but the difference is about the nature of the data. So, any question about this explanation on correlation so far? Any question?
No, doctor.
So is everybody clear with the explanations?
Yes.
Okay, thank you. So let's look at this table. Yeah, I've said correlation lies between plus or minus 1. So the nearer the value of the correlation to 1, the stronger the relationship. So what do I mean by this? If you have a value of, let's say, 0.6 to 0.9 something, you know 0.6 to 0.9 is moving closer to 1. That means you have a strong correlation between the two variables. 0.6 to 0.9 or 0.95, 0.98, because when you get to 0.99, it's almost perfect, 1. You are so close to 1. So that means the correlation is strong. The relationship between the two variables you are considering is so strong. When the correlation coefficient is going towards 0, let's say 0.000001 up to 0.039, you know, that is coming towards 0, then we'll say there is a weak correlation between the two variables. What does that mean? That means the correlation is suggesting a non-essential. That means the contribution is small between the two variables. The contribution is small when it is weak. But there's something we call, because that is how correlation is rated, something moderate, which lies between 0.4 and 0.59. You know, we said 0.6 and upward is strong, 0.4 downward is weak. But between 0.4, 0.5, you know, these are average scores, can still be considered as moderate relationship, moderate association. However, as I said before, the direction indicates whether it is negative or it is positive. So the direction here is not something that's called for worry. If correlation shows a negative correlation, what it means is that the relationship between the two variables is inverse. Remember in secondary school mathematics variation, when something is directly varies or partially varies or inversely vary. So when you have a negative correlation, you have an inverse relationship. What it means is that when one increase, a change in one will lead, an increase in one will lead to a decrease in the other. So it's a negative correlation. It's an inverse relationship. So it gives us the sign that when this one is increasing, this one will be reducing. So it could be a useful relationship. For example, in investment markets, when you have two assets and you correlate the two assets, maybe in terms of return or in terms of risk, maybe when the risk of one is increasing, the risk of other is decreasing, or the return from one is increasing when the return from others may be decreasing. So they use such relationship to combine assets in the investment market so that both assets will not be moving in the same direction. They will move in opposite direction so that at any point in time, each one will be countering the effect of the other. If there is a loss, the one that has increased, the increase, which is a gain, will counter the effect of the loss. So, and if one is increasing in gain, the one that is going down is moderating the gain from the other, so that the investment combination can balance. So the direction become immaterials, but what we are interested is the relationship strong or weak? If there's a strong relationship, that shows you that the two affect the other seriously. So if one, and this is again, this is common when we are looking at substitute goods. Goods you can substitute for another, or foods you can substitute for another. When price of one food goes up, you look at the one that can give you the perfect substitute, but at a lesser price. Because when the price of one goes up, the price of another comes down. So this is just what correlation is trying to depict, to tell us in the market that when you want to combine assets, asset that goes on opposite direction will be good to combine in a portfolio. And again, it makes us to understand what happens to different investments when there is a change in the market. And how does this investment interact with each other? So it helps a lot. For example, we all know in real estate world that when the income increases, the demand increases, either for consumer goods or for even durable goods like properties. So when income increases, it is known that the demand increase and price of goods will increase. Because more demand will pull up the price. So if you compare it with our property investment, when there's more income, the rent or the price of our property will increase because there will be more demand for properties, either in the rental or in the actual purchase or ownership. So we can now look at the relationship between income and prices of goods or rental market. So when the price increase, does it really increase the rent? If it doesn't increase the rent, does it really increase the price? Because there are some times, because rental market is a bit stable, that the price doesn't change quickly. But if it is in sales market, in property, when more money are coming in, more property prices can go up. And for example, now that because of the COVID, we are experiencing a fall in revenue, a fall in income, it is already affecting the sales price of properties. Developers are offering discounts. There are some price slash. I read over a couple of days ago that even I think Cyberjaya area, that the prices are becoming moderate for people because of what the effect of COVID-19 has done in the market, in the economy generally. So there are various ways of looking at different relationship among variables. Again, we can look at students and look at how they perform in both calculations, subject that has calculations, and subject that are composed of explanations, that you write stories than in calculation. So you can say that the more calculated or the calculation oriented a student is, the less writer such student will be. We can study it. So what do? We take this course of students in calculation oriented subjects like statistics, like valuations. So like development appraisals, where you need to do a lot of calculations or financial accounting. We look at their scores. Then you look at the subjects where people need to be telling stories. So we try to know what are the performances in those subjects. Then we can correlate whether the more you are the better you are in calculation, the better you are in theory, or whether it is the opposite relationship. So these are the things correlation studies, and it helps a lot in taking a lot of decisions. So the chart I have here is just a chart that we can use to do our further analysis. Maybe on our tutorial day, maybe we can try the data that we have here on this chart and try and look for what the correlation coefficient will be. We can even try it if we have time at our lecture times to transfer this data, especially X and Y, on this table. Then we do the necessary calculations. We can use Excel. So when we get our by X by Y, we can now go and put it in this formula to really know whether we are getting there or not. So when we get the coefficient, correlation coefficient, we then will be able to say whether it is strong, whether it is weak, whether it is positive, or whether it is negative. Any question? Any question about this?
No, doctor.
Okay. I hope everybody is clear with it. So let's quickly look at, yes, the interpreting correlation. Yes, I think I've explained this, but the one I've not explained is the p-value. So, well, I've told you it could be negative or positive. It can be weak, moderate, or strong. So when we have gotten either positive, moderate, strong or negative weak or negative strong relationship. The next thing is how significant it is. So this boils down to confidence interval. This at this level, when the p-value is less than 0.5, then we are within the error level. So we are confident of what the correlation analysis has given to us. Those is a significant, it becomes a significant explanation. When it is not significant, especially when the p-value is greater than 0.05, we say it is non-significant. So the correlation can be strong, but may not be significant. That means it can be ignored. So the relationship can, that means without that relationship, something else can still go on favorably. So we look at, by the time we do some analysis in SPSS, I tell you where the p-value is so that we read the p-values. So there are ways of calculating the p-value, but we need not to bother ourselves with that. Because from correlation, we now calculate either the t-test or the f value. Then having getting the f values, we go on to use f values to get the p-value. And p-value will now give us, the p-value will now give us whether it is less than 0.05 or whether it is greater than 0.05. Then we decide whether it's significant or not. But normally, a p-value less than 0.05 is considered significant. Alternatively, there is statistical table. When you get your T or F values or Z values, you go to Z-score table. You go and look at your value where it is. Then from there, you will know whether it is significant or not. So, but since we are in the digital world, that will just give us a p-value, and once we have the p-value less than 0.05, we consider significant. When it is greater, it is insignificant. So that is how to interpret correlation table. Any question? Still okay? Yeah, any question? Are we still okay with it?
Hopefully, okay.
Okay, so by the time we do an analysis, we will see the p-value. So I will quickly go to regression now to explain what regression is all about, because they are working together. So regression, why correlation look at the relationship or association between two variables? Regression look at predictions of variables or determining a variable from another variable of a relation in a relationship. So when two variables are related, when one changes, what happens to the other? Because if they are related, we will look at what will affect the other. Just as we said about as I explained about income and rental or property values. I said when income increases, it is expected that the price will increase. And I also said most time rental values or rental or rents are most of the time a little bit stable more than the property value prices. So if there is more money, the price of houses can change drastically immediately, but the rent might not immediately change. Why? Because ordinarily, before the income increases, properties are occupied already at a particular contract rent, which might have been tied to a period, 2 or 3 years period, and you are paying the same rent over the period of the tenancy contract. So definitely the rent will not immediately respond to increase in income. But unlike that, property sales price can adjust. When people know that more money and a lot of demand is increasing, then you can change the price. So we may want to look at what, now we know the association, there's a relationship between the two, but at what influence, what is the prediction? What rate will the changes in X affect Y? By what percentage will a change in X affect Y? So if it is just for one variable, you know, if you want to do prediction now, if it is just for one variable, let's say a variable like age, and you want to predict what will be the age of the next person. So we can take the age of everybody in the class. You know, the variable is age, one variable. We can take the variable of everybody, the age of everybody in the class, and if I want to predict the age of the next person, I can use the average, the middle, or either the median, the mean, or mode to predict the age, the age of the next person. So as I said initially, if I have an average age of 22 in this class, that people in this class have an average age of 22. I may decide to predict that the age of the next person is going to be 22, which is the average. That's still a prediction, but it is based on one variable. So we use the average of the existing data to predict the next data point. And for example, when you have return from your investment from 20 years back, you have what percent year in, year out, what are the rate of return in real estate investment. You can use that by finding the average and put it as the expected return for next year. This is still one data point, one variable being used to predict itself for the next data point. So you can use it to predict the return even in the next 5 years. You just estimate the average. Also, you can use the mean, the mode. What is most occurrence? Oh, between the last 10 years, the property market has given 8.8% return for about 7 years out of the last 10 years. You can use the mode and predict the next year that the return next year will also almost be 8%. That is a prediction based on what has been happening in the previous years. That's what they call time series analysis. In the last time, this is what we have been experiencing. However, when it turns out to be two variables, that one has impact on the other, then we call it regression. Now, when we call it regression, even for a regression between two variables can equally be determined by their correlation, by the strength of a relationship. However, when we say one variable X is determining another variable Y, since they are just two, it is expected that regression line will be a linear one. So we'll be having a linear regression. So the difference is that correlation indicates relationship or association within variables, while regression predicts one variable from the data set of another. Are we okay? So for the variable X and Y, we have this relationship. y is equal to a plus bx. So what does this mean? That means that y is the variable depending on x. Y, meaning y is being predicted by values of x. X is the independent variable which is predicting variable y. So all this you will meet it when you are doing your research methodology, when you are going to do your academic project. Somebody can ask you which one is your dependent variable, which one is independent. And a, the small a here, is the y-intercept. Y-intercept means when there's no x. When x is 0, definitely bx will be 0. So what will be the value of y? So what I'm saying is, when there's no income, for somebody who doesn't have income, it doesn't mean you will not pay rent. It doesn't mean you will not pay rent where he's living. So the intercept will determine what will happen to y when x is 0. And the b we call gradient is the slope of the equation, which is a kind of coefficient of x on y. So I've tried. So this is what the linear regression equation looks like when there's no error attached. So the y is the predicted values, x is the one predicting y, b is the slope, and b can predict either negative or b can be negative or positive, y a is the intercept of y. So, and this is the equation, the way this is the chart below it, to show that when x is 0, there's always a value for y, and to also show that b can be negative or positive. The slope can be negative or positive. So, to calculate the intercept and slope of regression, this is the formula. So, and from this diagram, we can see change in y, change in x, which is going to be the slope. The slope b is calculated from this change in y over change in x. So if there's a change in x, what will be the change in y? So then we can get our a. A is when x is equal to 0, what is the value of y? That is the intercept. So at this, when this straight line cuts the y-axis, which it cuts the y-axis, so determines what will be a. Because when the x is 0, definitely y is equal to will be equal to the intercept a. So that is the intercept. So we put in our figure as well. When we have variable figures here, and we calculate our b and a. So we'll try and this during our tutorial as well. We'll come out with a data. For example, we would like to know the relationship between either the size of an accommodation and the price, or the rent of a property and the capital value. Remember, we have a formula in valuation that says capital value is a relationship between the multiplier YP and the net income. So that means net income has a relationship, has something to do with the capital value. So we can look at that and work out our B and our A so that we can draw the regression line. Or we can, so with that, we can also be able to predict what will be the value of a property when we have when we have the net income. And this is the theory behind multiple valuations. So, you know, we can do multiple valuation. There are software that you can just put the parameters and it gives you the value of all the properties. So once it has been established through regression that the net income determines the price, or the size determines the price. So once that has been done, then you can be putting the size of the size of the accommodation or the property, and it will be calculating the value for us. Again, we can put if we are using the size in square foot, we put the square foot, and based on past experiences, the regression line can be fixed. And once you are putting the prices or the income or the sizes, the capital value will be generated. And this is the principle under the mass valuation, especially for taxation purposes. When you are valuing a properties for rating, when you need to value a lot of properties at the same time. So there are models. And this is also what was used in hedonic price modeling. So we look at every characteristic, the prices, and put it in a hedonic regression. Then the parameters are being fixed and your valuation is being generated. So we can create a data of two variables, let's say level of education and salary. So we can find the coefficient that if you have somebody that has also level of education, we definitely know what will be the salary range. So these are the regressions or estimations that has been done to do multiple tasks or to do same tasks in multiple ways for a reasonable number of time. Any question? Any question?
Doctor, can you go to the previous slide?
Okay. This one?
The Y
this one?
is, Doctor, I think Doctor, you see the Y, the Y label as a dependent variable, right?
Yes.
And then the X is labeled by predicting variable.
X is predicting, yes.
But you can go to next slide. The Y is a predicted value.
No, yes, that's the predicted, the dependent, predicted.
So meaning that Y is a predicted and X is a predicting. Is it correct?
Exactly. Predicted is the same thing as dependent.
Okay, understood. Thank you, Doctor.
X is predicting Y. Comes predicted values or dependent values. They are still the same thing. Are you okay?
Yes, okay now. Thank you, Doctor.
Okay. So we will try and put in figure into this to try to do the estimate. Meanwhile, we will still demonstrate it in SPSS. At least correlation, ANOVA, and regression. We will demonstrate it in SPSS. If we are okay with the little time we have, let's quickly look at multiple. Let me say something about multiple regression. You know, multiple regression comes in when independent variables become more than one. You know, for example, I've just mentioned a size of an accommodation and price, and I mentioned income as a predicting variable. So the two of them can be put into an equation where we will look at Y being determined by the income the property is generating, as well as the size of the property and some other qualities. Another thing is services. Another thing could be quality of accessibility to the property or infrastructures around or services. So we have a lot of things. So this is where hedonic pricing model comes in, that everything that is capable of affecting the price is put into the regression, and the coefficient of each one is found. So if we have more than 2, 3, we call it multiple regression. So all these variables at the same time are simultaneously affecting or are simultaneously predicting Y. When that happens as a multiple regression, so the same applies, and we just write the equation as it is here, you know our x now is ranging, is no more 1, but we have many x, so we call it xi. I ranges from 1 to n. So, and this is what happens. This is what the equation will look like until we get to the end. So each and every predicting variable, we have its own coefficient, or we have its own slope, what we call B, the slope of the coefficient of influence. So when we do that, we can get the coefficient for each one of them and put it in an equation so that we will know variable x1, how much contribution does it have to y? Variable x2, how much contribution does it have to y? Variable x3, how much contribution does it have to y? And on like that until we get to the last variables. So in statistics, when we are going to do this, we try to screen the variables to know which one are really important in predicting y, because we may have more than reasonable number of variables. For example, if you have 13 variables determining an independent variable, how much of these 13s, how many of these 13s are really contributing strongly to the predictions? So we do it by finding their correlation to know what is the degree of association, to screen how many of these variables we are going to put into our regression equation. Having said that, then, so yes, we will do multiple regression. All this regression, will practice it again in the statistical packages, because we want us to look at variables, various ways of doing the regression. But again, I quickly want us to know how do we interpret the regression output. So how do we interpret the regression? I want us to quickly look at it before we close for today. So when there is a regression, especially when we use software for the regression, we have something like this, depending on which software do we use. We have some, what do we look for? Number one, we try to look for the R square. For example, in this chart, we see R square here, shaded yellow. Then we see R square at the other side here. Especially in all regression statistics, after multiple R, the next thing we do is R square. R square. So this R square has meaning. The R square is saying that the factor, the variable under consideration, is contributing 5.58. That means 58% to the predicted variable. So when we look at this particular one, what we estimated there is the house price. We were looking at the house price and the square feet. That means the size and the house price. Here, what it tells is that the square feet, that is the size of a house, is contributing 58% to the price of the house. That means the size alone, how big is the property, is contributing as much as 58%. So that means it's a factor to be reckoned with. So that this gives you an idea of what you need to do to have a better price in for your house. So that is the function of the R square. Again, you look at the coefficient. So when you look at this coefficient, when you look at the square feet, he said it is written here 0.10977. That means we are talking about 0.1977 effect. What does this mean? If there is 1 a change of 1 square feet in your house, the price will increase by 0.0109, and that means you will experience about 10% increase in the price. So if the square feet is increased by 1 foot, you will get 10% increase in the price. So this is how we interpret the result of regression analysis. Another thing we need to look at is the significance level. So by this significance level, it's telling you this is 0.01 here. This is telling us that it is a significant contribution. That means this contribution of square feet into the price of a house is highly significant. It's not something you can just overlook. So again, when we look at the other table at the other side, we have to notice something. Here, the R square is 31%. Yes. So, and I think this is about a stock market. Yes, this is about a stock market estimate. Consider it with a particular asset in the stock market. So that if there is a change in the stock exchange index, it will change the price of that stock, of the concerned stock, by 31.36%, which is 0.31 R square. So R square is telling us that the market contribution to the prices of the asset is 31%. Then when we look at the p-value, you can see the p-value is not significant. It's 0.12. So what this is saying is that this 31.36% effect on the stock price by the stock exchange estimate is insignificantly contributing 31%. So this is what interpretation of the regression output is always like. We look for the significance, we look for the R square, we look for the coefficient, the size of the contribution of the change in price and the change in the other factor. So these are the things we need to interpret when we have a regression. I put this one up so that supposing in an exam, you are just given a regression output and you are expected to come out with the regression model or regression equation for the asset concerned. We should know what we are looking for. And if the variables with the independent variables are many, each variables will be listed. Whether they are significant, each one by one will be listed, and then the joint effect will also be provided. We will look at that when we are doing when we do our own regression in our SPSS. We will try and find out multiple regression, how much of this data will be reported. The one I'm displaying here is just like one variable predicting the other, but we will try a multiple regression and see how coefficients are listed, factor variable by variable, which one is significant, which one is not significant in our own exercise when we do practical next Thursday by His grace. So, any question? I've taken us to what inferential statistics is all about, interpreting the regression, interpreting the correlation. So, inferential statistics is basically about drawing a sample and predicting or estimating the population parameters from the sample, from the data collected from the sample. Any question? So is there any other question? Hopefully on Thursday, we'll demonstrate on SPSS and some Excel calculations.
Is this topic important? Because it seems very hard to us.
It look hard. Hello?
Yes, it seems too hard to
Well,
understand.
by the time we begin to manipulate figures, we put in figures. I'm sure maybe we'll get more questions at that time, but I just take you through what inferential statistics, how important it is. It's an important concept. It's more important at this level when we begin to apply statistics, especially even in research, in the future, in projects. So all these are going to be part of the thing we will be using, tools we'll be using, depending on where we find ourselves in future. So we need to know about correlation. When they say what is the correlation between two variables, we need to know predictions when we're talking about regression. So predictions means that if you know the price of an item, how does that determine the price of another item? So that's the basic things, but these are the steps. We just need to know the calculation. We will demonstrate the calculation, but we now shift to software because you'll be using all these Excel, DS. You may not use SPSS as much, but you will use Excel, you use other econometric softwares, but all of them do regression. All of them do correlation. So we begin to interpret from that point of view. So I think we will do calculations on Thursday. I will try and find and come up with some data for us to do the analysis. And maybe we begin to do more interpretation. When you see the formula to calculate the regression, equation, and all those things, it's a bit complex, right? But once you put it in Excel, we can go through it one by one. Are we okay?
Okay, doctor.
Okay, doctor.
Any other question?
Doctor, I want to ask for the formula because there are a lot of similar formula so as long as the answer is correct, so the formula we can use that. Not really we have to follow your formula. Is that okay?
Of course, when you come out with your formula, as long as it is, definitely when you use the formula, there will be little or no difference. So there are just different way of expressing, and eventually will come out to the same thing. For example, I want to show you this. If you look at this formula has been proved to equal to the one at the front. You can see their parameters look a bit different, but it has been proved that whatever you get here, gets here. One thing is that some may be parametric, the other one may be non-parametric. So because in statistics, the data were divided into two, whether they are normally distributed or not normally distributed. If they are normally distributed, they are regarded as parametric. If they are non-normal, they are non-parametric. And that can be a little deviation from how the formulas are assessed. But all the same, they should be heading towards the same area. So in SPSS, when you want to do, especially for correlation, you will see different type of correlation, whether you want to use Spearman rule, you want to use swing moment, where there's about 4 different, and different authors have different little changes in their formulas. Okay?
Okay. Thank you.
Thank you. I hope you have signed your attendance in Spectrum. Please do so. Sign your attendance in Spectrum. And if you have done that, I think we can end the lecture today to meet on Thursday. I have a presentation tomorrow. I need to prepare for that. So thank you and keep safe.
Thank you.
Thank you, Doctor.
Thank you, doctor.
Thank you, doctor.
Please, you can, any statistics books you have, you can read through again and try to identify what we are talking about regression. I put some